Welcome to LIB Academy. In this video, I am going to take you through time-dependent Schrödinger equation and why there is a need for us to know this in quantum mechanics. This is video 11 on our playlist titled Quantum Mechanics. In our previous video, we learned that psi, which is a function of distance x and time t, equal c e to the power I a, or alpha here. So this is a general solution of an electromagnetic wave, where we said psi is a function that describes the behavior of electron, and it is a function of distance x and time t. So this is a general solution, and we said our alpha equal 2 pi into bracket x over lambda minus vt. So if we substitute the value of alpha into the wave function, our wave function becomes this. Minus 2 pi ivt. So substituting the value of alpha into the wave function, this is how our wave function looks like. Then now what we do next, we are going to incorporate the Planck-Einstein constant, which is V equal total energy of a system over Planck constant, and the de Broglie relation, or the Broglie wavelength, which is equal to Planck constant over linear momentum in the x direction. So now what we want to do is to just substitute the value of the wavelength here by h over px and v here by e over h. We are trying to incorporate the Broglie's assumption into the wave function, and then the Planck-Einstein constant, which contains the total energy of the system, into the wave function. So doing that, we get our wave function to be psi xt equals c e to the power 2 pi ix px, all on h e to the power 2 pi I e t slash h. Now this is what we get after substituting the value of v and lambda into the wave function. Don't forget that we are deriving the time-dependent Schrödinger equation in this video. So now the next thing we want to do is to differentiate the wave function with respect to time. So d over dt is going to give us, now this wave function has the time part and the distance x part, the time t part and the distance x part, right? So now what we want to do is to look at where we have the time term, right? We have the time term here. And how do we differentiate exponential problems? If we have e to the power u, differentiating this will give us the derivative of u multiplied by e to the power u, which is multiplied by everything. So let's do so. So we are focusing at where we have the time term. So now we differentiate this whole term with respect to t. Then what we get is this term becomes 1, right? They're supposed to be negative here. Okay. So differentiating this whole term with t will give us minus 2 pi I e. This term becomes 1 slash h, which is divided by h. And then we are going to add this whole term there. Okay, so minus 2 pi I minus 2 pi I e. T is no more there. I'm sorry, t should be there over h. This term should not contain t. So now we have this term here which has no t term. We just bring it there, and our c2, we don't have to forget it. C's will come there, and then 2, sorry, e to the power 2 pi I x p x slash h. So now rearranging everything, we get a derivative of the wave function with respect to time to be equal to minus 2 pi I e over h, then c e to the power, any of them can come first. So e to the power minus 2 pi I e t slash h, and this e to the power 2 pi I x p x slash h. No, now what? We can do something about this equation right now. If we compare this term from the c part to the right, you could see that this is basically like the wave function, right? Looking at this, the wave function here, c e to the power this, e to the power minus that. You could see that we have c e to the power minus that and e to the power that. So which means that this whole term here equals psi of xt. So we can replace this term here with psi of xt. So this should give us minus 2 pi e, the wave function xt. Don't forget, this is the derivative of the wave function, with respect to time. So now we are going to focus on this equation. We are going to rearrange this equation into this form. So which means we are going to arrange everything by trying a means to leave the total energy of the system with the wave function at the other side, and the remaining one to go to the other side of the equation. The remaining terms. So now what do? Let's multiply both sides of the equation by the reciprocal of this. So we are going to multiply both sides of the equation by the reciprocal of this term with the exception of e. So we are going to multiply both sides of the equation by h over minus 2, sorry, this will be minus h over 2 pi I, 2 pi I. So we are going to multiply that by both sides of the equation. Xt dt should be equal to minus h over 2 pi I multiplied by minus 2 pi I e I over h. E should be here, and then the wave function. So at the end of the day, you will see that this h here will take care of the h here, and 2 pi I will take care of 2 pi I here, right? Because they are minus, we still have a positive e psi of x and t here. And then we are going to have minus h over 2 pi I d psi t over dt equal e psi of x and t. So rearranging the result of the derivative of the wave function with respect to time gives us this. And if you could remember in our previous video, energy and then momentum operators derivation. This is the energy relation, right? Because we have an operator here, which is the energy operator, acting on the wave function to give us the total energy of the system and the wave function back to the idea of eigenvalue equations. So now we have rearranged our product of the derivative with respect to time into the energy, to get the energy relation or equation. So now we know our Hamiltonian operator. We drive it in our previous video to be the Hamiltonian operator equal minus h squared over 8 pi squared m d over dx squared plus ep xt. The Hamiltonian operator is the total energy of the system, which incorporates the kinetic energy, the kinetic energy of the system or the electron or whatever we are dealing with, and the potential energy exerted on that system by gravity or electric field. And this is the potential energy part. So the Hamiltonian operator can be expressed in terms of the Planck constant or the reduced Planck constant. And the same as the energy operator right here can also be expressed in the reduced Planck constant form or in the Planck constant form. So which way, any of them that you should make sure that if you are using the Planck constant, it should be throughout, right? If you are using the Planck constant here, then you should use it your Hamiltonian operator. If you are using the reduced one, you should be using it here so that everything will become very simple. I mean to say here we have the energy operator to be minus h over 2 pi I, right? And we know the relation of h cross to be equal to 2 pi. So now making h the subject here, we are going to get h equal h cross 2 pi. So you can turn this whole term here in terms of h cross. So wherever we see h here, we will substitute the value this term there. So it's going to give us minus h cross 2 pi here, all divided by 2 pi I, 2 pi I. So at the end, 2 is going to take care of 2, pi is going to take care of pi. We are going to get minus h cross all over I. So this term here is the same as this term here, right? So in some of the equations, they use this. So make sure not to get confused by that. If you know the relation between the reduced Planck constant and the Planck constant, you are good to go. However, there can be some sort of mathematical deduction to these two relations of I. So one of the relation of I is that there is a need to know these things. 1 over I equal minus I. And you should know that. So if 1 over I is equal to minus I, let's work on this here. So we can rearrange this term to be minus 1 over I multiplying h cross, right? So 1 over I is minus I, right? So let's bring the minus sign out here. So minus 1 over I h cross. So we can replace this 1 over I here as minus I. So this is going to give us, I don't know, let me write it somewhere here. 1 over I equal minus I. So we are going to replace here by minus I multiplying h cross. So this is going to give us positive I h cross. So in some relation or equations, you will see the energy operator here, h minus h over 2 pi I, to be just I h cross. So in that case, don't be confused. That was just by the way. So now we know our momentum operator. So what we want to do next is to replace, and we said the Hamiltonian operator, which is the total energy of the system. So what we want to do is that from our energy equation, we said this E here from Planck-Einstein relation is the total energy of the system. We are going to substitute E by the total energy of the system, which is the Hamiltonian operator. So let's do that. So we are going to write this term here, which is minus h over 2 pi I derivative with respect to time, and then our wave function xt equal the total energy of the system. We are going to replace E by this term. Substitute this whole term there as the total energy of the system. So we are going to get minus h squared over 8 pi squared m d over dx squared plus EP xt, and then our wave function xt. So let me turn the whole equation. Let me write this first. I'm going to make this as the right hand side, the left hand side, and this as the right hand side. So starting with this term, just want to make the presentation look m d over dx squared plus the potential energy term, the wave function is equal to this whole term here minus h over 2 pi I dt, the wave function t. So now let me talk about these two energy terms. This one here and that one here. That one there, English. So as we said earlier, this is the Hamiltonian operator, which represents the total energy of the system, and this the time derivative, which is the energy operator. This defines how that energy, the Hamiltonian energy, causes the state of the particle to change from one moment to the next, right? So that is the difference between this energy term and that energy operator. Yes, the total energy of the system and the effect of this on the system, which causes the energy changes. So now this is a time-dependent Schrödinger equation, but we are not going to leave it like this. Let's try and leave it in 3D. So leaving it in 3D, now we are looking at x, which is on 1D for now. Let's leave it in 3D. For in 3D, it means we are going to incorporate the y and z axis term. So it means that instead of this place to be the x squared, we are going to get, the x squared, a term containing the x squared, a term containing the y squared, and then the z squared, right? So this whole term, putting this whole term here can make our equation lengthy. So we represent this whole term by the Laplacian operator, which is just don't forget to square this term. So we are going to represent this whole term here by this. So now let's rewrite our equation again. So we are going to get minus h squared. So minus h squared over 8 pi squared m Laplacian operator squared, the delta squared, and then plus EP, the potential energy of the system, to also be in terms of x, y, z, and then t. And then the wave function to be here to also be in terms of x, y, z, and t. So equal minus h minus h over 2 pi I d over dt, and the wave function should be in x, y, z, and t. So this is the time-dependent Schrodinger equation, but it does have a general term to be this. So this is the general form of the time-dependent Schrodinger equation. You know, this is the Hamiltonian operator and the wave function, which can be in 4D or 3D, and then the energy operator changing with respect to time and the wave function. So the reason why we need to know this equation is it describes how the quantum state of the physical system changes over time. So there is a need to know this time-dependent Schrodinger equation and the time-independent Schrodinger equation because they are complementary. So we frequently use the time-independent Schrodinger equation to find the allowed energy state of a system and then plug the result into the time-dependent Schrodinger equation to see how the system dynamically evolves or moves as a whole. So in our next video, we'll look at how to derive the time-independent Schrodinger equation, and we'll move forward to see how to play around with these equations. That is it for this video. See you in my next video. If you found this video helpful, kindly subscribe to my channel and give a thumbs up to this video for more educational content like this. You can also refer my channel to your friends. Thank you. Bye.